Before I start, I just have one correction to make, erratum. So in the last lecture, just before proving Young's inequality, I summarized the results of LP of omega. So I wrote LP star of omega equals LP of omega by mistake. So this should be actually LP omega star. So 1 less than or equal to P less than infinity. Okay, so this is the correction which you should do. Okay, so today we will do some exercises. So first one, 1 less than or equal to P, Q, R less than infinity, such that 1 by P plus 1 by Q equals 1 by R. If F is in LP mu, so throughout we will have excess mu is a measure space. I will not specify it every exercise because it's the general hypothesis. So if F belongs to LP mu and G belongs to LQ of mu, show that Fg belongs to Lr of mu and that norm Fg in Lr is less than or equal to norm F in LP, norm G in LQ. Okay, solution. So you have that 1 by P plus 1 by Q equal to 1 by R. Therefore, you have that R is less than P and R is less than Q. So P by R is bigger than 1, Q by R is bigger than 1, and 1 by P by R plus 1 by Q by R equal to 1. Okay, so this is, so now if you take integral over x mod Fg power R d mu, okay, so that is equal to integral over x mod F power R mod G power R d mu. Now F is P integrable, so this is F power R is P by R integrable, and similarly G power R is Q by R integrable, so we can apply Helder's inequality. So this is less than or equal to integral over x mod F to the R power P by R, that is P whole power 1 by P by R, so R by P, into integral over x mod G power R to the Q by R, so that will give you Q d mu whole to the power of R by Q. So now you take the rth root on both sides, you get norm Fg R, so this is finite, and therefore Fg power R is integrable, and norm Fg R is less than or equal to norm Fp norm Gq. Okay, so that is the solution. Okay, second is also so we have, let F from x to F belong to LP of mu. Okay, you define HF of T is equal to the measure of mod F bigger than T. Recall, mod F bigger than T is the set of all x in X such that mod Fx is bigger than T. So this is a measurable set, and therefore its measure can be defined, and so this is called in fact the distribution function of F. Okay, so then norm Fp, so show that norm Fp whole power p is equal to p times integral 0 to infinity t to the p minus 1 hf of t dt. Okay. So solution. So let us take the right hand side, p times integral 0 to infinity t to the p minus 1 hf of t dt. So this is equal to p times integral 0 to infinity t to the p minus 1. Now what is hf of t? It is a measure of some set. So you can write integral over x chi of mod f bigger than t at x and then dx dt. Okay, so you have this integral over x is nothing but the measure. Integral of characteristic function gives you the measure of the set, so this is precisely what you have as hf of t. Now everything is non-negative, so we can interchange the order of integration without bothering about anything. So this is equal to integral p integral over x and now integral over t, so dt dx. Okay, now t goes from where? T is non-negative, that is seen from here, and this tells you that t can only go up to mod f, so 0 to mod fx. Those are the limits of the integration, and then t power p minus 1 dt dx. Now p t power p minus 1 is t power p, so this is equal to integral x of mod fx power p dx, and that is decided d mu, not dx, d mu, and d mu of x actually to be correct. Okay, so that this is nothing but norm fp whole power p. Okay, so that is this. Third one, A. Let fn converge to f almost everywhere. All functions are measurable. I am not mentioning that. There's no point talking about otherwise. So gn converge to g almost everywhere, and mod fn of x less than or equal to gn of x. And also assume that integral over x gn d mu converges to integral over x g d mu, which is given to be finite. So all these are hypotheses. Then show that integral over x fn d mu converges to integral fd. So this is a generalized dominated convergence theorem. In dominated convergence theorem, you would have fn's are all bounded by a single g and g is integrable. Now you are relaxing that. You are saying fn is bounded by gn converges to g and g is integrable. Okay, so this is called the generalized dominated convergence theorem. So let us first solve this. So solution. So mod fn is less than or equal to gn. So this implies gn plus fn is greater than or equal to 0 and gn minus fn is also greater than or equal to 0. So we can apply Fatou's lemma. So what does Fatou's lemma say? So gn plus fn goes to g plus f. So integral g plus f d mu over x is less than or equal to lim inf of integral over x gn plus fn d mu, but gn actually converges, so this is equal to integral g d mu over x plus lim inf integral fn d mu over x. Similarly, integral over x g minus f d mu is less than or equal to lim inf integral over x Gn minus Fn d mu, and again Gn converges, so this is equal to integral G d mu minus lim inf becomes lim sup of integral over x Fn d mu. Now integral G d mu is finite, and therefore we are allowed to cancel it in both these relationships. So if you cancel that, so you will get integral f d mu is less or equal to lim inf integral Fn d mu, and that of course is always less than or equal to lim sup of integral Fn d mu. But lim sup here, if you take it to the other side, if you interchange the positions, so this becomes less than or equal to integral x f d mu. So you have a sandwich in which either end is the same. So this implies lim inf equals lim sup equals this. Therefore this implies that limit n tending to infinity integral Fn d mu over x equals integral f d mu over x. Okay. So B, we are going to use this to get a nice result. So let 1 less than equal to P less than infinity, and Fn f belong to LP of mu. So you already know both of them are an LP of mu. Then and Fn converges to F almost everywhere. Then norm of Fn minus F P goes to 0, that is Fn converges to F in LP if and only if norm Fnp converges to norm Fp. So this is a useful result, because you have, if you know that both the functions are in LP, that is Fn and F, and if Fn goes to F pointwise and the norm converges, this is usually easier to show, then you have that it actually converges in the LP norm. Okay, so this is a very useful result. So this way, so solution obvious, because norm is a continuous function. So if Fn converges to F in LP, this implies that norm Fn P goes to norm F. So that is in any norm linear space, that is true. So you don't have to do much. So now we are going to do the converse, which is the interesting part. So Fn goes to F almost everywhere, and you are given that norm Fnp goes to norm Fp, and you have to show norm Fn minus F in LP goes to 0. So let me define capital Fn to be equal to mod Fn minus F power p. So by hypothesis this goes to 0 almost everywhere, and then by convexity this is less than or equal to 2 power p minus 1 mod Fn to the p plus mod f power p. So this is convexity of t going to t power p. Or mod t power. Okay. Okay. So I am going to call this. So this is by this I am defining as Gn. Then Gn goes to G, which again I am defining as twice 2 power p mod f power p. Because Fn goes to F almost everywhere, so you get 2 f power p, there is a 2 here, and therefore this is definition of G. And also you have that integral G d mu is finite, because integral of G is just 2 power p integral f power p, f is in LP, so we are using that information. Okay, and also integral Gn d mu over x goes to integral G d mu over x, and that is precisely we are using this part of the hypothesis. Okay, so therefore you have that all the conditions of the previous part are true, and therefore integral fn goes to 0. So this implies integral fn goes to 0 d mu over x, that is fn minus f in LP goes to 0. So this proves the converse. Okay. 4. So 1 less than equal to p less than infinity, fn goes to f in LP mu, and gn goes to g almost everywhere, and mod gn, mod g are all bounded by a fixed constant. Then fn gn goes to fg in LP. So again, these kind of theorems are very useful because we want to know the convergence of integrals. That is what is the key thing in all this. So solution. So norm fn gn minus fg in P by the triangle inequality is less than equal to norm of fn minus f gn in LP plus norm of f into gn minus g in LP. Okay, so let us take the first one, norm of fn minus f gn in LP. Okay, so what is this? Power p. This is equal to integral mod fn minus f power p mod gn power p d mu over x, that is less than equal to m power p integral mod fn minus f power p d mu over x, and that of course we have given is goes to 0. Now what about f integral f gn minus g p power p? So this is equal to integral over x mod f power p mod gn minus g power p d mu. So mod fp mod gn minus g power p goes to 0 pointwise. That is given to us. Also, it is less than or equal to, so mod fp mod gn minus g power p is less than or equal to 2 power p m power p mod f power p, and this is integrable. And therefore, by dominated convergence theorem, we have norm f gn minus g p goes to 0. So each term goes to 0. So fn gn also goes to fg in LP. So we have shown that this goes to 0. We have shown that this also goes to 0, and therefore